Great, cool. Hi, everyone. I'm Dimitris, and I'm a cryptography researcher at Nilion. This is my first CAMLIS, and I'm very excited to be here today. I will talk about curl, private LLMs through wavelet-encoded lookup tables. And this is a joint work with Manuel, Mehmet, Stanislaw, José, Shubho, and Miguel. So if you haven't heard about Nilion before, focus on privacy-enhancing technologies. And one of those technologies is called secure multi-party computation. And with MPC, we can do the seemingly impossible task of actually computing on private data without seeing the data. So what this looks like is that we can have a client send their data in a privacy-preserving way to some servers, and then the servers can perform a computation on the data without actually learning anything about the data. And this is very useful because it has many applications. I hope this is visible from in the back. This is threshold signatures that are very popular with cryptocurrency wallets, or in the context of this, this conference, privacy-preserving machine learning. And I want to focus a little bit more on MPC, to give you some kind of background through an example. I got rid of one of the servers to simplify my animations here. So assume that we have 3 clients, and each has their private data. And now our task, or the task of the servers, is to compute the sum without looking at the client's inputs. And an easy way to do this would be for each client to secret share their data, as we call it. And this is done by creating a random number and subtracting it from their private number, sending one number to the first server, the other number to the second server. Now, the servers receive the data and maintain a private sum, and this happens for every client. And as this goes through, the servers update the sums, and at the end, you will notice we have ended up with secret shares of the final result. And throughout this process, the servers did not learn the client's private inputs. At the end, they can just exchange those shares and learn the final result. All right? This was quite simple. And I want you to take my word for it that we can similarly do multiplication. It's a little bit more complicated, but there are many resources out there, and I urge you to look this up if you haven't seen this before. But taking my word for it, now with additional multiplication, we can actually do machine learning inference, which is really interesting. And to draw an example here, the motivational example, assume that we have a server on the left-hand side that owns a private model. And then on the other side, we have another server that owns some private inputs. And what we can do here is that neither of the servers want to compromise the privacy of their data. So what we can do is secret share the inputs in a similar way that our clients secret shared their private inputs before. Then the other server can secret share the model, and then they can work together to run privacy-preserving inference on the private data of server 2 using the private model of server 1. Well, not quite. It's not as simple, and I want to walk you through some of the steps to make this possible. The bottleneck in MPC is when we try to evaluate some nonlinear functions, and these are quite useful for machine learning, unfortunately. And here I'm talking about logarithms, GELU, activation functions, and so on. So one way to evaluate these nonlinearities is by encode them as circuits, right? And then evaluating the circuit. But this has to be very large and ends up being quite expensive. So let's rule this out. An alternative, and this is quite popular in the privacy-preserving machine learning literature, is to actually do a polynomial approximation, like a Taylor series and so on, to approximate the nonlinear functions. But unfortunately, although they work quite well for small models, like when we go into large language models, they incur high errors and they're quite inefficient because they require a lot of communication. There is a solution, and it is using lookup tables. So we can use a lookup table and encode the inputs and the outputs of these nonlinear functions. And then there are some MPC protocols that allow us to evaluate a lookup table with our private inputs. This is getting there, but still not quite efficient because in order to get high accuracy for our LLMs, then our lookup table needs to be very large, which yields a lot of communication, and this makes everything impractical. Right, that was kind of a long introduction. So everything leads to our framework, where our goal here is to essentially make this lookup table smaller to be able to evaluate them under MPC and have while maintaining high accuracy. And we do this with a technique that's called discrete wavelet transforms. We propose two protocols. One is called hard DWT, and the other one is called bi-orthogonal DWT. The hard DWT is simpler and faster, but does not approximate as well as the second one. And the second one, the bi-orthogonal, is a bit slower because it's more complicated, but achieves lower errors. And to benchmark our framework, we compared against related works for a set of nonlinear functions, and we also evaluate different LLMs. So I mentioned the lookup tables before. This is kind of a technical slide, so this will be the only one though, so let's go through it. Let's assume that we want to evaluate a logarithm. We have a lookup table that has 5 logarithms, top right, and we have the values for the logarithm. Server 1 will have a secret input, let's say 4, and the first step would be to secret share this input, as we saw before. Before we do that, okay, yes, this is the intended output of the protocol. So the first step would be to secret share the input, as we saw before. So the server 1 picks a random number, sends it to server 2, and holds the difference. For this protocol, we will also bring a trusted third party to help us generate some randomness. So this party, we call them the dealer. So the dealer will generate a random number, secret share it to the two parties, and then use it to create a one-hot vector with the 1 being at the position of this R. The dealer will also secret share this again to the two parties, and then we won't need the dealer anymore. From now on, the two servers can run an MPC protocol to evaluate the public lookup table. And here's how this works. They can subtract from their private shares of X the private shares of R, and compute these shares of delta. And then this delta can be made public because the random number from the dealer actually masks the private input. So this does not reveal anything about the input. Now that we have this random delta, we can use it to rotate our lookup table. And you can see from top right to over here, we have like a rotated lookup table of the logarithms. And then the two servers can compute a dot product between the one-hot vectors and this rotated table, and then end up with one-hot vectors that in the one-hot position, now it's the intended value. And of course, these are all random numbers, so they don't really know which is the position of interest. Finally, they can just sum everything up, and they end up with secret shares of the intended output. All right, so now that we have an understanding of how we can evaluate a lookup table in a privacy-preserving way, so this is an overview of how the DWT works. And our realization here is that any signal using the DWT can be split into some approximations and some details. And then if we keep doing this multiple times, at the end, we will get a very good approximation that, as you can see, has the same pattern as our original signal, but is missing a lot of the details. And for smooth functions, these are mostly the functions of interest in machine learning, we can actually get rid of the details. And what is very interesting here is that every time that we have applied this DWT technique, if we have encoded the first signal as a lookup table, now every lookup table that we create for the approximation is half the size of the original one. So we still end up with a very good approximation, but significantly smaller. So going back to our original question of how we evaluate nonlinear function with a lookup table, let's say, of 32 bits, so, well, this is not quite possible. So the direct evaluation, let's rule it out because it's prohibitively expensive, especially for the purposes of LLMs that require many of them. Then an alternative would be to quantize the input. Let's say starting from 32 bits, we just get rid of 16 bits, and we evaluate a smaller lookup table and end up with 16-bit outputs. So this can work, but this has high errors and very bad approximation, like when we, in the purpose of an LLM. Now, putting in the DWT and the lookup table protocol, we end up with our first variant, which is hard DWT, that starting with, let's say, 32 bits, we can keep the MSBs. And now, instead of looking up any lookup table, we look up on a DWT-encoded lookup table. In this, the difference with before is that here the output is 32 bits again. So this effectively yields a significantly better approximation already. And then when we go to the bi-orthogonal DWT, there are more things going on here, but overall, I want to give you the intuition that here we do 2 DWT lookup table lookups, and we also use some linear transforms, and by putting everything together, this ends up being a bit more expensive, but yields a higher accuracy. Next, we observe that this already achieves better accuracies compared to related works. We realize that in certain functions, we can do some further optimizations. For example, some functions are bounded. So outside of some range, x left and x right here, they converge to a constant. So what we can do is that we can create our lookup table only within this range, and then do a secure comparison to see if our input lies within or outside this range. And if it's within, we will just look it up in our lookup table. Otherwise, we will fix it to the constant. The second realization was that some functions, again, have a symmetric point, and the values on the right-hand side of the symmetric point are the same as on the left-hand side of the symmetric point, but like flipped. So what we can do, instead of encoding the lookup table to be this red area, we can have a smaller lookup table, and on the same size of lookup table, we can pack way more values, so we further get better accuracy. So how this looks in terms of performance and errors, we compared it with Crypten, which is a privacy-preserving machine learning library from Facebook. So the mean average error here of Crypten is constant for different lookup table sizes. And so here we show increasing lookup table sizes. And for our errors go down with the bigger lookup table sizes that we use. And at the same time, the bigger lookup table sizes require more operations. So like our runtime increases. But overall, for lookup tables smaller than 2 to the 7 entries, we achieve lower errors than Crypten and higher performance. Similarly, we observe this for different activation functions that were not possible in Crypten. And here's a table that we also include in the paper of all the results and the comparisons we ran against Crypten. And what I want you to focus on, like the highlighted areas, is essentially where our framework is better than Crypten. In terms of latency, lower is better. Communication rounds and total communication, again, lower is better, and errors. Finally, we created 5 different language models, starting from a small BERT Tiny up to a GPT-Neo. And these runtimes for this community might seem a lot, like 3.5 to run 64 tokens on the BERT Tiny, but keep in mind that this protects both the model and also the input sequence. And give you some context, we also compared with related works for BERT base for 128 tokens, and our framework was the fastest, had the lowest total rounds of communication and the lowest total communication by a big margin. Lastly, to wrap up, lookup tables are very important, and they have enabled a lot of different applications in privacy-preserved machine learning and in MPC. One of the problems is that to actually get really good approximations, we need to use very big lookup tables. So here we used discrete wavelet transforms to make these lookup tables smaller, while achieving high accuracy and at the same time lowering the communication, which in effect makes the whole process faster. As a side note, we use the same technique in a different privacy-enhancing technology, which is called homomorphic encryption, of using DWT for the lookup tables. And this work was presented recently on the Information Security Conference. And that wraps it up. Happy to take any questions.
Great job, Dimitris. Yes, we'll pass the mic around. I'll start with a question about, so the approximation that you're using with the wavelet transform, could you go back 2 slides? Yeah, this kind of result. In other areas where we're approximating models with distillation or truncation of weights and things like that, the thing you want to look for is that the model isn't doing any worse at natural language understanding or anything like that. Have you checked that? Does this approximation to activation functions change anything?
In terms of accuracy, you mean?
Performance, yeah.
Yeah, so we performed some experiments with BERT-tiny and BERT-base. And like our accuracy was almost matching plain text accuracy.
Mm-hmm.
The models we had were not super, trained.
Mm-hmm.
So I think it was like 91% on plain text, and we were achieving 90% on encrypted.
Yeah. Cool.
This.
Great. Any other questions? Ed in the back.
I really enjoyed the talk. So the MPC works better if all your components are linear or linear-ish is a common theme. I'm wondering if obviously this helps you make a better MPC setup. I'm wondering if it also helps you make just sort of a better, like, tiny, fast model. If you did this in a non-private setting, is this like ridiculously fast, or does it really only benefit us in the MPC setting?
That's a good question. I haven't thought about it before, so take what I say with a grain of salt. When you don't have secret shares, so like everything is in plain text, I don't see any reason of looking up a value in a lookup table instead of doing the evaluation directly. Now, if looking up a value is significantly faster than in doing a softmax or a GELU, then it might be worth it. Trade-off that this will introduce some errors, right? But instead, if it gives any performance overheads, any performance enhancement.
All right, thank you.
One in the front here.
A question in terms of your setup, and forgive me, I'm a little dated on MPC, but there's a notional assumption of sort of the Byzantine problem underlying all this, where you have to have fair players. Are you assuming both of these are fairly computing for privacy, or are you dealing with the adversarial dynamic?
Yeah, that's a great question. I skimmed over all these details due to the interest of time. So there's a term of how we need to quantify how the parties, the servers, are acting. And there are different models. So the most common model, especially in industry, is the semi-honest model, which means that the parties are interested in learning something about the data, your hidden data. Like one party wants to learn the model of the other party, and the other party wants to learn the inputs of the other party. But they follow the protocol specification. So when they are supposed to add something, they will actually do the addition. Then there's another model that's stronger than this. It says these parties will also try to cheat, to either change the output of the protocol or to learn something some private input of the other party, which is called malicious. We focus on the former. So we assume that both parties will behave honestly. Yes, and we protect the privacy.
Okay, semi-honest was the, yeah, okay.
Great. Well, thank you very much, Dimitris.
Thanks.